Two landmark studies for optical genome mapping are out this week. We talked to the lead author on the papers next on Mendelspod. Welcome to the program. I'm Therrell Timpson. Anyone familiar with our program knows we've been tracking the progress of genome mapping over the years. This past week, the technology achieved a new milestone with the publication of these two papers in the American Journal of Human Genetics that have demonstrated 100% concordance between optical genome mapping and traditional cytogenetic techniques, including karyotyping, FISH, and CNV microarrays. Dr. Alex Hoischen from Radboud University in the Netherlands is the lead author on the papers, and he joins us today to talk about these papers and why this is big news. Today's podcast is brought to you by Bionanogenomics, the structural variation company. Bionano reveals more information for your genomics research. Welcome to the podcast, Alex.
Thanks so much. Pleasure to be on this show. Thank you, Tara.
So over the past decade, next-gen sequencing has made big inroads into the clinical laboratory. We're all pretty familiar with that. Now it sounds like optical genome mapping will be an important technology when it comes to next-generation cytogenetics or looking at the chromosomes. What was the main goal of this paper?
Both papers are proof-of-concept studies to show that optical genome mapping can compete with the standard of care technologies for cytogenetic testing. And those are karyotyping, FISH, and CNV microarrays. Those are standard of care and so far have not been replaced by any sequencing approach. So there's still a desperate need for novel technologies that can do so. If you go to the most extreme, like karyotyping, that basically still is a standard of care technology that hasn't changed largely since 50 years. So it's about time to change that. And in these two studies, I think we gave a first glimpse that optical genome mapping is on a really good track to do so.
Could you just give us some background here on classical cytogenetics and how it's been done and what some of the challenges have been?
So if you start again with karyotyping, I think one of the challenges there is that you need viable cells. And the training to have a cytogenetics lab up and running really requires intensive training. So it's really highly skilled people that can do karyotyping. It's really recognizing a chromosome by its bending pattern. And that is, if you wish, almost an art. It's really not trivial. I tried that in my very early master work, and I never really mastered that technology. It really is almost like a gift with very intense training. But if you're so skilled, then you really can get very good results for that, and therefore it remains standard of care for so long. I think the biggest caveat of karyotyping is its resolution. You really can only see if there's a missing chromosomal band, if the entire band is missing or large chunks of a band are missing. And as such, the resolution is somewhere in the range of 5 to 10 megabases. So millions of base pairs that need to be missing or need to be inserted. And obviously, we know that much smaller insertions or deletions in the genome can already cause severe disease. So we desperately need technologies that have higher resolution. That came roughly, 20 years ago, close to 20 years ago with CNV microarrays. I think they really were picked up rapidly in the clinic, really for diagnostic care, because they simply offered a much higher resolution. Almost single exon resolution is the latest standard for that in clinical care. However, these CNV microarrays had a few caveats as well. Next to missing balanced events, CNV microarrays also cannot tell us where gained material is in the genome. So we can identify a chromosomal gain, but we don't know whether that is a tandem duplication or whether material is inserted at another spot of that respective genome. So all of that usually was answered by karyotyping or FISH in addition to the CNV microarray. So in a lot of cytogenetic laboratories, we needed the mix of technologies to answer all questions. Mm-hmm. And there, I think there's some of the attractive bits of optical genome mapping, because here our studies demonstrate that very likely optical genome mapping can replace all 3 standard of care technologies in one go.
In one test.
In one test, indeed. So as such, the testing laboratories would look much easier, could be much more streamlined, and I think also man hours would be much lower once we really get it going routinely.
Yeah, so let's get into that. So what are the highlights of this study?
So first of all, the 100% concordance for both constitutional aberrations. So those are chromosomal aberrations that are present at birth. And the same holds true for the maybe even more challenging acquired aberrations that we see in leukemia or other hematological malignancies. So for both, we reach 100% concordance for the aberrations that were clinically important in all samples tested. So I think that is the big highlight.
So that means the mapping is picking up 100% of all of the variants.
Correct. Of all of the variants that have been in our previous clinical report, so all the aberrations that were clinically meaningful. Indeed.
Yeah. So that's really exciting.
That is exciting, yeah. And maybe different from other tests or technologies that we've tested for such a purpose in the past, also the process was relatively straightforward and easy. The analysis is relatively trivial. You don't need to have a computer science degree to analyze the data, and you don't need a big team of bioinformaticians to pull out the data. We just did it with a commercially available software that comes with the system. So that means our lab technicians or staff members in diagnostics can really do the analysis themselves. And that again is similar to what they used to already from the CNV microarrays. It's really just clicking a few times and you look at the entire genome of your sample. Importantly, what I think I'm also excited about, and also particularly my colleagues in diagnostics are excited about, the search space is not really huge, different from some sequencing approaches. What I mean with that is that it seems to have a very low false positive rate. And with relatively straightforward and already established filters, we can get down to the clinically relevant aberrations relatively straightforward. And again, there we can really learn from the experience that we have from CNV microarrays and other cytogenetic assays in the lab. So as such, I think we would not need to change a lot of our workflows and interpretations in our clinical setting if we would replace all the tests by optical genome mapping. And I think that is really useful and very, very exciting.
So it's quite quick and acts quite targeted, you might say? Or how would you?
In terms of the analysis, so the beauty is, as karyotyping, it's a genome-wide approach, also similar to CNV microarrays, but we can do the analysis in a targeted way to, for example, for leukemia, only look at the well-established leukemia driver genes and whether they are involved in aberrations in our test. Mm-hmm. So I think that is quite attractive and makes analysis relatively straightforward. And it also prevents you from searching in unknown variants for too long. So it prevents us from looking at so-called variants of unknown significance. Right, we can really target it to the ones that are well established.
Right, that's been a problem for whole genome sequencing. When you just head out there into unknown territory for too long and getting all
that those... That is correct. I mean,
yeah,
you're absolutely, that's spot on. Although I should add, also for genomes, you could implement similar filtering strategies, but at least so far, that has not been as straightforward.
Now, when you're using optical genome mapping, is there any reason to do any sequencing?
Good question. I think we should clarify one thing here. So I think optical genome mapping is extremely good to identify structure variants in the genome. So those are larger chunks of DNA that are aberrant. However, it will probably never have the ability to identify point mutations. So as such, sequencing is really will continue to be the routine test for point mutations for sure, and probably also for indels. Current resolution of optical genome mapping starts at 500 base pairs. Everything below really requires a sequencing approach. But I think if we combine optical genome mapping and sequencing, may it be short-read sequencing, such as Illumina, or long-read sequencing, such as PacBio, and combine it with optical genome mapping, we may reach near-perfect genomes. So if you really want to get everything out of a genome, all the variants that are really present, I think the combination of mapping and sequencing would really yield something that people could consider the gold or even the platinum quality genome.
Yeah. Okay. So what we're talking about now is key benefits of the optical genome mapping over traditional methods and even over trying to bring in next-gen sequencing. But the other one that we haven't really mentioned enough maybe is with these other methods, you would have to combine methods, right, for a complete approach.
Very good point.
And this is just one test.
Mm-hmm. So if I just allude as an example to the leukemia study or the study on hematological malignancies, the average sample we retrieve from a patient suffering from leukemia gets more than 5 tests in our laboratory. So it very often is the combination of karyotyping, CNV microarrays, and multiple different FISH probes are tested to find all the balanced translocations, for example, sensitively. And that is obviously very laborious. It's even requiring different expertise in the lab, different lab protocols to get all that going. And now it seems that optical genome mapping could potentially replace all of those tests in one go. So if the average leukemia sample gets 5 or so tests, we could just replace it with a single test and still get the same results, but potentially even more complete and even faster.
Are there limitations or challenges for the genome mapping?
Yeah, obviously. So, and I'm happy to allude to some of the current challenges with that. So at the moment, optical genome mapping is not yet able to identify balanced translocations if the breakpoint happens in the centromere or pericentromeric. So it seems that the structure of the human centromeres is so complex and probably not even well understood in the reference genomes up until recently, until the Telomere to Telomere Consortium released some of their data that were fairly incomplete, full of gaps. And I think mapping data to the centromere still remained a major challenge. So that is currently not possible, and we excluded those type of aberrations purposely from both studies so far. So I think that is one shortcoming. A second one for leukemia is that the CNV microarrays we use routinely can detect so-called regions of homozygosity, or rather loss of heterozygosity. So those are homozygous stretches in the cancer genome, in the leukemia genome, that by using SNP microarrays, we can detect fairly easily if they are large chunks. That is not yet implemented in the Bionano software, but we pulled out the data ourselves and were able to visualize them. So I hope that will be implemented more routinely also in the optical genome mapping software soon.
Oh, okay. But both of those could be addressed at some point.
I have to be honest, the centromeric breakpoints remain an issue. And that is only for balanced translocations. So I think they're so complex that we really need to see data in the months and years to come, whether that really can be resolved.
I see. Okay. Yeah. So now the question I have is now to this week with these studies coming out, what will this mean going forward? Do you think for this field, for cytogenetics? There's a term we use when we talk to clinical lab people here on the podcast, and that's standard of care. It comes up all the time when we're talking whole genome sequencing. When do you think this might become standard of care? Do you think it will? What's your thoughts?
So I should declare that I'm fully hired in our research division, not in our clinical or diagnostic division.
Okay, all right.
However, that was one of the purpose of these manuscripts. So I did not only want to put the manuscripts out, but also convince my colleagues in diagnostics. Mm-hmm. And they were so convinced by these 2 studies, which were both retrospective studies. So we just went back to aberration positive samples. But our management team and our diagnostic unit were so convinced by these early data that they now decided to finance a clinical utility study. So we will run optical genome mapping in parallel to the standard of care test in a prospective manner now.
Okay.
I expect that simply resembles very much what we've seen so far. But as such, a clinical utility study run by my colleagues in diagnostics will also include looking at time for analysis, cost per sample, turnaround time, and all those other important metrics for diagnostic use. And once that study is completed, which I expect to be within a couple of months from now, then I think we dare to say whether this could really be a diagnostic or standard of care assays soon.
Okay, so that's still got to be done.
At least in our laboratory, I think.
Yeah, that's the next step.
Yeah, that's the next step for us. I know that there's one or two other laboratories that are already using it in parallel to standard of care assays in the clinical setting right now. And I think that every country has slightly different regulations around that.
Sure.
And again, I'm fully hired by research, and therefore maybe I'm even more optimistic than a few others, or less conservative maybe. I'm fairly optimistic that this will enter clinical care not too soon from now. My best guess would be that we will see several labs within a year using this in a clinical setting.
Yeah, and so put your optimistic hat on. How do you see that playing out? What would that look like?
So for me, I think, especially for the hematological malignancies, the data is so convincing and the workflow gets so much easier that I think we will, after the prospective study, will be convinced that this is the way forward. And then probably we will continue to run optical genome mapping in parallel to the standard of care assays for the time being, and learn on the flight, and then simply replace it at some stage.
Right. Okay. So you'd run the traditional classical methods alongside with it for a while, just to verify. Sort of like they did in the early days of next-gen sequencing. They were still running some Sanger sequencing to verify.
That's exactly what we did. I mean, we started with exome sequencing here as a research tool in 2009 and 2010. And we did the first diagnostic exomes in 2011. And indeed, 2011, 2012, we still did a lot of Sanger validations up until we saw that it's really not needed. And often NGS, especially for point mutations, look better than Sanger sequencing. And I foresee something very similar for optical genome mapping.
Yeah. Okay. So how do you think it might impact research? You're on the research side. Does this open up any new possibilities in research?
Oh, yeah, absolutely. So that is not part of these two papers, but we just have two other manuscripts accepted currently on hidden structural variants that have been missed by a lot of the standard approaches. So those are structural variants that remained hidden in some occasions for, I think, 20 years in one family. And now by optical genome mapping, we identify the hidden structural variant that causes disease.
Right, because one of your points in the paper, it was that it not only had 100% concordance, but it was finding more. And there was actually, it was doing more complex work.
Yeah, that is true. That is true for the clinical samples. I think we're closer to the real underlying biology to understand the aberrations more completely than any of the other tests alone, or possibly even in combination. And then also for the research, we see that the standard assays we use there, again, those are usually exomes or even genome sequencing, sometimes CNV microarrays, they are not perfect yet. So they miss occasionally structural variants. And they, I think, is something, a core strength of optical genome mapping. It's really irrespective of the sequence context, we can approach regions of the genome that were really difficult to read or reach into by other methods such as sequencing. So obviously now we went back to some of our unsolved rare disease families, and we already have the first successes there. So far, I can tell you that we've run roughly 20 different projects, and 5 of them are already solved.
Wow.
And for the others, we are still looking into some of the data, but 5 out of 20 have been solved successfully, and that is more than I expected initially. So that is a very nice and positive surprise, telling us that optical genome mapping, as one of the really ultra long read technologies, can really reach into regions that were difficult to assess previously.
Wow, that's great.